All right, what I want to do in this video is talk about activation energy and also how the reaction rate depends on the temperature. So first things first, activation energy, what is that? Activation energy is basically the minimum certain energy required that the molecules must possess. So you can consider this to be a threshold level of energy that should be possessed by the molecules so that they can collide with each other and give you successful collisions which lead to products. So for any reaction in general, you would be able to draw an energy profile where y-axis has energy, x-axis has reaction progress. So you go from reactants to products. In this case, since my products are lower in energy than the reactants, I would say that this is going to be an exothermic process. That means the delta H is going to be a negative number, but realize that it requires energy to go through an activation barrier, and that is what is called as the E-act or EA. Usually is reported in kilojoules. This is always a positive quantity because it is an energy required. So just a red flag there. If you have to calculate that in a test and one of the numbers that's given to you is a negative value, check your math, or in a dry lab, as the case may be. This depends only on the nature of the reaction. It's independent of the temperature and the concentration. And basically what it tells you is that the reaction is going to be pretty fast if this activation energy is small, because that would mean that the molecules can cross over onto the product side pretty clearly, easily. On the other hand, if you have a very high activation energy, that would mean, oh my goodness, we are trying to get there, but guess what? We keep falling back. So it's very difficult to cross over the energy barrier in that case, and we would say that the reaction is going to be extremely slow. So this is a fast reaction, this is a slow reaction. Now, let's see if we still remember order of the reaction. The question is, for the following reaction A plus B giving you C, if I double the concentration of A and hold B constant. So we are keeping this constant, we are doubling this. The rate doubles. So if A doubles, R doubles. What is the order with respect to A? So hopefully you can see it's a linear relationship. The order should be 1. It would be 2 if it would have quadrupled, and it would be 0 if there is no change in the rate. So recall that, don't forget about that. Order of the reaction and dependency on a certain reactant is kind of the central thought of this chapter. Anyway, let's go forward. Now, I'm trying to go over a concept here where I'm trying to show you that there is a reaction, let's say A plus BC, and that gives you products AB plus C. So for a reaction like that, realize that several things have to happen. Essentially, the bond between B and C has to break, and the bond between A and B has to be made and finalized, and only then AB will be formed and C will be liberated, right? And all this does require some energy, and the amount of energy that is required, we say that that's the activation energy. In this case, again, we call this an exothermic reaction because the energy of the products is less than energy of the reactants. But realize that molecules will have a tendency to try to get to the transition state, and they'll keep falling back, and they'll try again, and they'll keep falling back until and unless there are some molecules which go over on the other side. We don't say that the products are going to get formed. All right. Now, later on, we are going to discuss catalysts, and catalysts basically function by lowering of the activation energy barrier. So in that case, you will see that the energy barrier will start looking kind of like that. And essentially it's basically the speed of the reaction that gets altered. No change occurs in the extent of reaction because both the forward and backward reaction get affected by the same amount. So we'll discuss that in chapter 13 and 14, but realize anytime you see a lower activation energy, that basically means that reaction is facilitated pretty well, and that reaction is going to occur fast. So you should know which reaction is slow, which one is fast by, if graph is given. Likewise, you should know where the reactants are, where the products are, whether it's exo or endothermic. So an endothermic will look something like that. And then, of course, activation energy, transition state, all of that good stuff. All right, so let's discuss the effect of temperature on the reaction rate. Well, first things first, I mean, if you think about it, the rates of chemical reactions in general are considered pretty sensitive to temperature. For example, if you run a certain reaction at room temperature and then you start heating it at, you have an increase in temperature by maybe 100, by maybe 10 degrees Celsius or so. The increase in the rate would be typically, by double the amount. So the rate doubles for every 10-degree rise in temperature. But the question is, why is it? How do you explain? Why is it that as you increase the temperature, the effect on the reaction rate is dramatic? And the answer to that goes back to the rate law and how the rate law connects to temperature. So let's consider a generic reaction. You have A giving you some products, and we're used to saying that rate is equal to K times concentration raised to the power of some order M. Right, so the concentration and the order, those are related to the reactants, of course. But what is K? K is the rate constant, and recall we always write this for a specific temperature, T. That means that if I change the temperature, the value of K is going to change as well. And so the temperature dependence of a certain reaction rate is sort of contained in this rate constant K. And an increase in temperature generally would increase the value of K. So increase in T means increase in K, okay? And so that basically culminates in a faster rate. So far so good. Now in this whole dependence, essentially, this was worked on in the 19th century by a very famous Swedish chemist by the name Arrhenius. He's the same guy who also worked on Arrhenius acids and bases, remember, from Gen Chem 1? He's the same guy. And he gave a certain law. He said that the rate constant essentially can be seen to be equal to a product of a frequency factor times exponent of negative EA over RT, where EA is my activation energy, R is my gas constant, so that's 8.314 joules per mole per Kelvin. T is the temperature in Kelvin. And A he called was essentially a frequency factor. Now I'm going to go over, what each of this means, and K, I think I defined that first, but again, it's rate constant. I'm going to explain this to you through an example. Hopefully what we have discussed so far, that if there is a reaction going from reactants to products, the minimum amount of energy, you can call it the energy barrier, you can call it the energy hump, whatever you want to say, that must be surmounted for the reactants to be transformed into the products. So all of your molecules must have that kind of energy to get converted into the products. We will give it a name. It's the activation energy, right? And essentially one can envision that as the molecules are going from the reactant side over on the product side, essentially they will go through a phase of bond breaking and bond formation, which is going to yield, which is going to generate what is called as transition state or activated complex. activated complex or transition state, either of the two. Okay, now let's discuss an example. Let's say you have CH3 and a C. So that's my methyl isonitrile, and I want to convert it into CH3CN, which is acetonitrile. All right, so envision what has to happen. Essentially, the bond between the carbon and the nitrogen, so this guy right here, this has to weaken, right, until the CH3 would break away, and then this CH3 will have to somehow attack the carbon right here, so it has to bind to that. So there is one bond that needs to weaken and break away, and there is another bond that needs to get formed. Both of those things have to take place. So if you were to apply this scenario onto my energy profile I'm showing you, you can say that the CH3 and C is on the reactant side, the CH3CN is on the product side, and perhaps you can even envision that the TS, the transition state, is where the bond breaking from the N and the bond formation with the carbon is what is going to take place. Now, and of course, the energy required to go through this process, we call that the activation energy. Realize that every single time molecules kind of, rotate, and this bond between the carbon and nitrogen, it kind of wags a little bit to go through that bond weakening. So it's trying to get to the transition state. It may or may not have the energy depending on the collisions, and so it might fall back, and then it'll try again and then fall back, and maybe one fine day or one fine moment it will get the energy and it'll go across on the other side. Now the one and only the one where it was able to go across on top of that hill, that activated complex hill, we would say those are the ones that are going to give you fruitful collisions, and they are the ones that are going to generate the product. So the part where we say the frequency factor, the A, frequency factor, or A, essentially is dependent on the material that you're using, which ones are breaking, which ones are being made. It depends on the system, but realize that this particular factor essentially reflects the number of approaches to the activation barrier. And what that means is that species are they're trying to get to the activated complex. They haven't quite reached the activated complex. And so it's not equivalent to surmounting it. The two things are actually different. The other thing that I want to talk about, I said that K is equal to e to the power of negative EA over RT. We talked about activation energy, we talked about the frequency factor. I want to talk about the exponential. What do we mean by exponential? Realize this is going to be essentially a fraction between 0 and 1. If you have a system where your energy of activation is very low and the temperature is very high, hopefully you can see that it'll be a less negative number, and that would mean that this will be a number pretty close to 1, right? On the other hand, if the energy of activation is really high and the temperature is really low, then that would make this factor extremely negative, more negative. So it will be like saying that rate constant is equal to e to the power of negative infinity. So that's going to turn out to be 0. So one can say that in that particular case, your exponential factor is going to turn out to be 0. On the other hand, if if we do have e to the power of 0, then that will tend to 1. And that basically means that every approach to the activation barrier is successful. So that's like saying, even though it's only theoretical, not practical, there is no hump at all. It's like saying there is no hump at all, right? Because every time molecules collide, boom, the product gets formed. That's what it means. Now, as the temperature increases, essentially, the kinetic energy of the molecules increases. So realize that if you were to plot perhaps the fraction of molecules versus energy, it essentially is a bell-shaped curve. Okay, and this is at some temperature, T1. And as you increase the temperature, T2, it flattens out a little bit. Well, what does that flattening mean? Suppose you have a reaction for which you require a threshold energy of 100 kilojoules, right? What that means is that at temperature T1, maybe that T1 is only 50 degrees Celsius, it had only this area in red that I'm kind of shading out. That is the number of molecules that have sufficient thermal energy to go through the transition state. On the other hand, as you increase the temperature, now you have given energy, you have pumped energy to the system, the kinetic energy increases, and so now, of course, your kinetic energy will increase, and so at a higher temperature, more and more number of molecules will have sufficient energy, that threshold energy, in order to go through, in order to make it to the reaction, and so that is the reason why your curve is going to flatten out. Okay, so realize that small changes in temperature sometimes will cause large differences in the number of molecules having enough energy to go through the activation barrier, and that hopefully explains to you the sensitivity of the reaction rates to temperatures. So realize frequency factor that we talked about, which is the number of times that the molecules would try to interact and try to achieve the transition state, but trying to achieve and actually achieving, those are two different things. And as we are increasing the temperature, we are basically we are providing the kinetic energy, and hence the probability of going through on the other side of the hill, of the energy hill, that is going to be greater at higher temperatures than otherwise. I hope you're with me so far, and so let's go forward. And so Arrhenius's plots, which were experimental measurements of frequency factor and the activation energy, those were kind of, calculated, and essentially an equation was provided, which as a 1-point equation is given as natural log of k is equal to natural log of a minus ea over rt, where a is the plot of or natural log of a is essentially this number right here. This is going to be a constant which is going to depend on the material in question, and T is of course the temperature. In Kelvin, R is the gas constant, E is the activation energy. So one can say that this is of the format Y is equal to mx plus b, where if you try to plot the natural log of k versus 1 over t, then it should be a negative curve, the slope of which should be negative ea over r, because that's the slope, and the intercept right here is going to be natural log of a. So you should be able to determine the value for any given system if required. Okay. The Arrhenius equation can be derived in a 2-point format also, because one can say if this equation holds true for one temperature, so let's say this is natural log of K1 is equal to natural log of A minus EA over RT1, we can have another equation where we could say natural log of K2 is equal to ln A minus EA over R T2. And so if this is equation 1, this is equation 2, I could simply go 1 minus 2, or you can do 2 minus 1, whichever you like, it doesn't matter. So natural log of K1 minus natural log of K2, natural log of K2 is equal to natural log of A minus EA over R. Hopefully you can see I can take that common, so 1 over T1 minus 1 over T2, and there is a negative EA. I'm sorry, natural log of A, those two get cancel off. Since there is a negative sign on the right hand side, I can multiply the whole equation by a negative sign or by minus 1, so that will look like natural log of K2 minus natural log of K1 is equal to EA over R, 1 over T1 minus 1 over T2. And since these are both natural logs, you can say natural log of K2 over K1. K1 is going to be equal to EA over R, 1 over T1 minus 1 over T2. The one thing you have to keep in mind is that the temperatures are in Kelvin, so if they are not, you need to take the time to convert it before you would be able to use that. Okay? Let's see if we can actually apply that to a problem. The question is, for a certain reaction, the rate constant doubles when the temperature increases from 15 to 25. So that's the 10-degree change that we were talking about. Calculate the activation energy. That's the first thing. The second question is calculate the rate constant at 100 degrees Celsius, taking K at 25 degrees to be 1.2 times 10 to the power of negative 2 liter per mole per second. So hopefully you can see a couple things here. The rate constant doubles when temperature increases from 15 to 25. So if this is T1, this is T2. Let's make sure that we convert it right now to Kelvin so we don't forget about it. 298 Kelvin. And the fact that we are given that the rate constant doubles, that basically tells you that if K1, the first rate constant was K1, then K2 is going to be twice K1. In other words, the relative relationship between K2 and K1 is 2. We already know that from this question. So Arrhenius's two-point equation that gives us natural log of, since there are two temperatures, that's what I need, K2 over K1 is equal to EA over RT, or EA over R, 1 over T1 minus 1 over T2. Natural log of K2 over K1, I just figured that that was 2. EA is what I'm seeking. R is 8.314. 1 over 288. 1 over 298. Solve. Realize that the units for R are joules per mole per Kelvin. Of course, your temperature is going to come out to be in 1 over Kelvin. So the Kelvin and Kelvin is going to cancel off from here. Kelvin and Kelvin are going to cancel off. And essentially, we are going to get an overall value in joules, which you will have to convert into kilojoules because that's what the activation energy is usually reported in. Okay? So just to kind of solve, I'm going to use the space. Natural log of 2 is, let's write that again, 8.314, 314. 1 over 288, that's like 0.00347 minus 1 over 1 divided by 298, that's 0.00335, and this is natural log of 2. Natural log of 2 is 0.693 is equal to EA 8.314, and then the subtraction, whatever that comes out to be. So let's calculate EA, how much that's going to become. I'm getting a value 48013.4 joules per mole. So in kilojoules, you divide that by 1,000, and that will come out to be 48.01 kilojoules per mole. The next part is calculate the rate constant at 100 degrees Celsius, taking K at 25 to be 1.2 times 10 to the negative 2 liter per mole per second. Realize the units of K will be exactly the same. So we are going to just punch in the same Arrhenius 2-point equation. K2 is what I'm seeking. Rate constant is what I want. So K2 is what I'm seeking. The K1 value is given to be negative 2. And you should use the units so that you know what it would be at the end of the day. Activation energy we just calculated, and you can write it in the joule pattern or the kilojoule, as the case may be. Since I have 8.314, I wrote it in the joule format, and temperature T1 is 298. From that, I'm going to be subtracting 1 over 373, and we have to solve for K2. Okay, that's what we have to do. The one thing that I would kind of suggest to keep as a checkpoint for yourself is that you're increasing the temperature. And I gave you the relationship a couple minutes ago that as you increase the temperature, reaction is going to go faster, more kinetic energy. So K should increase. That means the value of K should be higher than the 1.2 times 10 to the negative 2. So just keep that in mind, okay? And when you solve this, it's coming out to be 3.86 on my calculator. And when you try to solve that, you can hopefully say that since if it is natural log on the left hand side, you're basically saying that that is going to be equal to K2 divided by 1.2 times 10 to the negative 2 is equal to e to the power of 3.86. And that value comes out to be 47 point something, 0.4. When you multiply that by 0.012, you have a number 0.569 liter per mole per Kelvin. Notice this number is higher than 0.012. So of course it's a higher number. That makes sense, that as you're increasing the temperature, the rate is going to increase as well. All right, the question is, if I increase the temperature of a reaction from 110 Kelvin to 120 Kelvin, what happens to the rate of the reaction? Hopefully you can see, irrespective of Kelvin or degrees, since the size of a Kelvin is same as the size of a degree Celsius, essentially 10-degree change means the reaction rate should double. All right. Okay, the last thing that I want to talk about is the orientation. So I've been talking about the activation barrier or the energy of activation, that's the minimum threshold of energy that is required. The other thing you want to discuss, you want to consider when you're thinking about getting the fruitful collisions is the orientation of the reactant molecules. So for example, if you have, let's say, NO, okay, NO. So that's nitrogen and this is oxygen, nitrogen and oxygen. And that has to react with Cl2. Okay, and the product is supposed to be NOCl, NOCl. So realize plus Cl. So realize the bond has to be between nitrogen and chlorine. Now, if you say that NO moves in this direction and Cl moves in this direction, boom, reaction occurs. No, that orientation is improper. Why? Because currently oxygen is the one that's facing the Cl, so the proper bonding is not going to take place. On the other hand, if we flip, and oxygen is at the back, and nitrogen is the one that's at front. And now the two Cls come in. Yes, the reaction will occur because in this case the proper orientation is going to be present. So realize both of these factors, that the activation barrier as well as the proper orientation, which essentially defines the frequency factor in the Arrhenius equation is what is given by what is called as the collision model, that only those collisions will be effective and will give rise to the product if they have the suitable activation energy as well as the suitable orientation between the reactant molecules. Not every molecule, not every collision is going to give rise to your final product. Okay.